So now we're going to use the ideal gas law to figure out the pressure of the oxygen. So we have the pressure of the oxygen times the volume, which this is our new volume inside of our tank, is a 5-liter tank, is equal to N, our number of moles, which is 0.49 moles, times R, which is 0.08206 liters times atmosphere over Kelvin times mole times the temperature, which is 298 Kelvin. Then we're going to then divide both sides by the 5 liters to solve for the pressure of the oxygen. So in your calculator, you've got open parentheses 0.49 times 0.08206 times 298, close the parentheses, divided by 5. And we have 2.4 atmospheres for the pressure of just the oxygen. Now we need to find the pressure of the helium. So we have the 5 liters for the tank. We've got 1.9 moles of helium. We've got R, which is 0.08206 liters times atmosphere over Kelvin times mole times the 298 Kelvin. We're going to divide both sides by the 5 liters. And our pressure of helium is equal to, we're going to do open parentheses, 1.9 times 0.08206 times 298, close the parentheses, divided by 5. And that gives us 9.3 atmospheres for the pressure of helium. Now, we need to figure out the total pressure inside of the tank. In order to figure out the total pressure inside of the tank, we're going to take our pressure of oxygen plus the pressure of helium, and that's going to give us our pressure total. So that's going to be 2.4 atmospheres plus 9.3 atmospheres, which gives us 11.7 atmospheres for the total pressure inside of the tank. One more problem here that's similar to what we did in the lab. We've got a sample of solid potassium chlorate. It was heated in a test tube and it decomposed according to the reaction. I'm going to go ahead and rewrite the reaction for you since the subscription transfer. We've got 2 KClO3 yields 2 KCl plus O2. The oxygen produced, so this is diatomic oxygen O2, was collected by displacement of water at 22 degrees Celsius. So we've got a temperature of 22 degrees Celsius. We have a pressure total. So the resulting mixture of both oxygen and water vapor had a pressure total of 754 torr. It's good to make note that that's the pressure of the oxygen plus the pressure of the water. And we need to calculate the partial pressure of just the oxygen. And we need to know how many moles of oxygen we have present. It tells us that the pressure of the water vapor is equal to 21 torr. So here we're going to use Dalton's law to calculate the pressure of the oxygen. So we know our pressure total is equal to the pressure of the oxygen plus the pressure of the water. We have 754 torr, and that's equal to the pressure of the oxygen, which we're looking for, plus the 21 torr, which is the pressure of the water. We're going to subtract 21 torr from both sides, so 754 minus 21 gives us a pressure of oxygen that is 733 torr. In order to be able to use this to figure out the number of moles that we have, we're going to first have to convert this into atmospheres. So we know there are 760 torr in 1 atmosphere. So when we divide by 760, 733 divided by 760, that gives us 0.964 atmospheres for the pressure of the oxygen. So now we're going to use the ideal gas law again. PV equals nRT. We have the pressure of the oxygen is 0.964 atmospheres. We have a volume of 0.650 liters is equal to some number of moles of oxygen that we don't know. We have 0.08206 liters times atmosphere over K mole. And our temperature is 22 degrees Celsius, so we're 22 plus 273 is going to give us 295 Kelvin. To isolate N, we're then going to divide both sides by 0.08206 liters times atmosphere over Kelvin times mole times the 295 Kelvin. So N is equal to, so and we're going to open parentheses 0.964 times 0.650, close parentheses, divided by open parentheses 0.08206 times 295, close the parentheses, and we get 0.026 moles of oxygen.